Sarabjot?
Okay. Yeah. Quoting Richard Feynman, out of the cradle onto dry land, here it is standing, atoms with consciousness, matter with curiosity, stands at the sea, wonders at wondering, I, a universe of atoms or an atom in the universe. A highly energetic morning to one and all connected with us today for this short-term course on Advanced High Energy Physics 2020. Reverend Director Sir, worthy guest of honor, Professor Rohini Godbole, respected HOD Ma'am, Dr. Haleen Dhaya, honorable faculty members, and my dear physicist friends from all over India, I welcome you all to this knowledge boosting platform. This 5-day e-course is designed as a beautiful amalgamation of different areas like astroparticle physics, experimental techniques for particle physics, covering baffling topics like neutron stars, dark matter, standard model, and many more. The value of high energy physics is threefold: transformational science, technological impact, and production of highly trained scientists. From the invention of World Wide Web to Higgs boson, human consciousness and pursuit of the unknown have enabled us to tame the myriad of mysteries. Although still a lot is unexplored, unexplained, and unreachable. This course is a tiny step towards the light, beyond the evanescent wisp of atmosphere, the endless depths of cosmos. I now invite our ever-inspiring HOD Ma'am, Dr. Haleen Dhaya, a passionate high-energy physicist herself, and also the convener of this course, to shed light on the details of the course and welcome the participants. Ma'am, please.
Thank you, Sarabjot. Good morning, everyone. I am very pleased to be here today to extend to you all a very hearty and warm welcome on behalf of the coordinators of the course, Dr. Arvind Kumar and Dr. Sunil Dutt, and the Department of Physics, NIT Jalandhar, for this e-STC. I consider it a very special honor to welcome Professor Lalit Kumar Awasthi, Director, NITJ, as our inspiring mentor. Under his far-sighted vision and support, NITJ has evolved amongst the highly ranked institutions. We have in him a very strong leader who is leading this institution dynamically. He has always been persuasive to faculty members to think big, which has led to optimism and self-confidence in the faculty members. We will always be indebted to you, sir, for your contribution to NITJ. We also welcome the registrar, Dr. Shushendra Mishra, for showing his interest in physics and all possible logistics. He has been instrumental in making many positive changes in the institute. We would like to extend a special welcome to our guest of honor, Professor Rohini Godbole, who would be speaking shortly. I have known Rohini since my PhD days, and I still remember the energy and enthusiasm her presence would bring to any meeting or discussion. She was and still is a source of motivation for many researchers, especially women. I'm also thankful to you for accepting our invitation and agreeing to deliver a talk. I'm sure the young researchers will gain a lot from you. I also feel very happy to see so many colleagues and students. We are without a doubt especially grateful to you to join us here today. So this course will bring together leading researchers to lecture on their specialties and provide an opportunity to define critical problems of current interest. We have around 14.
Yes, now you're back. You're back on.
Okay. So there was some, Okay. So wish you all the best. Thank you.
Thank you, ma'am, for leading our way. We are in the cosmos. We are of the cosmos. We are a way for universe to be in awe of itself. I now request our worthy director, sir, Dr. L.K. Awasthi, to oblige us with his pearls of wisdom. Sir, please.
Good morning. Greetings from NIT Jalandhar, our esteemed expert and speaker for this session, Madam Rohini Godbole ji, Dr. Haleen Dhaya, Dr. Arvind Kumar, Dr. Sunil. Good morning to all of you and welcome. So, on behalf of NIT Jalandhar and on my personal behalf, I welcome everyone, all participants, to this online e-STC on advances in high energy physics. As you all know, this institute came in 1987 as Regional Engineering College Jalandhar. Later on, this institute became a deemed university, National Institute of Technology in 2002, and later on it was rechristened as Institute of National Importance. Ever since its beginning, it has been having pursuits mainly towards technical education, science, and then management. So we have grown from 100 odd students to roughly 4,500 students now, offering 11 undergraduate courses and 16 postgraduate courses. The institute takes usually 125 research scholars every year. There are many good things which has happened to the institute due to the tireless effort of faculty, student, and staff. We have been ranked 52nd in NIRF, and we are in Atal Innovation ranking. We are in A band with many IITs and few NITs as well. And institute has filed more than 25 patents and designs during this year itself. So this year has been a year of innovations and maybe for technology dissemination, because the institute has organized more than 25-30 such courses, short-term courses, webinars on different aspects of engineering, technology, science, and management. This course has been perceived by our physics department, and as everyone knows, the high energy physics, this has got a lot of our applications, maybe the applications in scanning and maybe in medical and many more things. And then it help you to find out the origin of the universe, how we originated. So many things. And we have the list of experts who will be enlightening all 1,400 odd participants for this short-term course. I congratulate Department of Physics. I thank Madam Godbole. As a educationist, I put 30 years. I feel that the education system in India is having few problems, and those problems are that in spite of all our efforts, we are not able to reach, or we are not able to deliver at international fora in the terms of the different research pursuits which we are taking, and we somewhere have left behind the creativity, innovation, and looking at the fundamental aspects of our problems and research. So the problem solving and practical knowledge, that should be somewhere at the beginning of a student when he starts his graduation studies, or even before that. His mind should be trained to how to handle the problems. And one more aspect is that the institutions like NITs, IITs, and IISc, for that matter, they need to come up, they need to form big teams and good teams, so that people can come together, and the good knowledge which the generation behind is having, that can be transferred, and very nicely it can be put in use. So thank you. And I wish that everyone connected will be able to learn about high energy physics. Thank you. Jai Hind, Jai Bharat.
Thank you very much, sir. Today, we are fortunate enough to have our esteemed guest of honor, Professor Rohini Godbole, amongst us, who is an epitome of women's strength in the field of science, a recipient of Padma Shri in Science and Engineering, Nuclear, 2019, an elected fellow of all 3 Science Academies of India and also the Science Academy of Developing World. Professor Godbole is currently working at Center for High Energy Physics, Indian Institute of Science, Bangalore. She has worked extensively on various aspects of phenomenology, particularly Standard Model, at the Physics Beyond It. She obtained BSc from Sir Parshuram College, University of Pune, MSc from IIT Mumbai, and PhD in Theoretical Particle Physics from State University of New York at Stony Brook in 1979. She joined Tata Institute of Fundamental Research, Mumbai in 1979 and then served as lecturer and reader at Department of Physics, University of Bombay from 1982 to 95. Later, she joined IISc Bangalore and has been professor since 1998. She has authored more than 150 research papers, with many reaching the zenith of citation indices in her area. Apart from her academic commitments, she is also a part of International Detector Advisory Group from International Linear Collider at CERN. She is the chairperson of Panel for Women in Science Initiative of Indian Academy of Sciences. She has published many books, Leelavati's Daughters, Theory and Phenomenology of S Particles, to name a few. With innumerable feathers on her cap, Professor Godbole has indeed brought laurels to Indian science fraternity. I now request her to share her aspirations from the young scientists of India and her thoughts for this course. Ma'am, please.
Thank you very much. So, Dr. Awasthi, the director in ITJ, then Dr. Harleen Daya, who indeed I have known for many years, as well as Dr. Arvind Kumar and Dr. Sunil Dutt, who are organizing this e-STC course. Let me begin by thanking you for inviting me to give this flag off your STC, e-STC program. And what I will do is that I will share my screen in a second. And afterwards, if the network becomes unstable, I might just switch off my video. So, and in case the contact is lost and I keep on talking and you people can't hear me, please give me a call, because these things happen in these programs. So I am sort of really impressed with the number of people who have registered for this course. Right now, at least I see 184 who have joined on this Google Meet program. So I welcome and all my friends. So let me try to now share my PDF file. Let's see if it works. Let me know if you can see my entire screen.
Yes, ma'am. Yes.
Okay, very good. So, as was already said by the MC Sarbajit Kaur and also by your director as well as by Harleen, particle physics is a very interesting beast, in the sense that for development of all around development of this subject, you need people who can think about mysteries of universe theoretically on just theoretical front. Then you need experimentalists who will actually build the detectors, which are sometimes, I will show you a few pictures, which are really the engineering marvels. And even more importantly, they also need a big contribution from people who build accelerators, who accelerate particles to very, very high energies, to velocities, rather close fraction of velocity of light. So particle physics is indeed a subject where all the different ways of doing science meet each other. And therefore, I'm very happy that this particular program about advances in high energy physics Can people hear me? Because suddenly I was told that I'm not presenting.
Yes, ma'am.
Can you still hear me?
Yes, ma'am.
Okay, because my
Absolutely, ma'am.
good. Because my computer told me I was not sharing. Okay, fine.
But ma'am, screen is not sharing.
Actually, ma'am, somebody tried to share his screen, and that actually created a
So
problem.
then maybe I'll try to share again. Okay.
Yes, ma'am, and we will try to fix that. Nobody is able to share
All right,
except you.
all right, all right.
Thank you.
Because I just got a message saying that,
Sure. Sorry, ma'am, for that.
no, that's
Please,
okay. I
please.
mean, this happens. Actually, I am now getting very familiar with all the glitches that happen in e-presentations. That's why I asked you this question.
Okay, ma'am.
Because the other day I was at a conference and the speaker kept on talking and nobody could hear or see. So,
Okay, ma'am, your screen is visible now, ma'am, again.
very good. All right. So as I was trying to tell that I am really, really pleased that there is this program of advances in high energy physics in an institution like NIT Jalandhar, because otherwise sometimes people get this feeling that high energy physics is just an esoteric subject which a few people should pursue in the confines of their rooms. But actually this is one subject where cutting edge technology, cutting edge engineering, and cutting edge theory all come together, and that's where we can all join hands together in solving the puzzles of the universe. So what I have decided to do is I'm going to talk about status of particle physics, and then there is a subtitle after the Physics Nobel Prizes of 2013 and 2015. So first I will tell you what were the two Nobel Prizes. The Nobel Prize of 2013 was for the discovery of the Higgs. So this was the discovery which was the final piece of information to prove that the currently accepted description of elementary particles and interactions among them, namely the standard model, is the right one. So that was the Nobel Prize of 2013. Whereas Nobel Prize of 2015 was given to the discovery of neutrino oscillations. And I will explain as we go along what is meant by neutrino oscillations. It gave proof that there must exist physics, either particles or interactions beyond the SM, and for the SM is standard model, and the physics, or that is interactions and particles beyond the standard model, is called BSM physics. So the two Nobel Prizes, as you can see, one Nobel Prize was to show that standard model is indeed right, and the second Nobel Prize is the one that I'm talking about. It's also to say that there must exist some physics, some particles, some interactions beyond the standard model. So already those of you who don't have time or interest can go home, because this is the message that these two Nobel Prizes keep particle physics in a very exciting state. So what is my plan? I will first tell you about these two Nobel Prizes very briefly. Then I will also tell you what were the questions that were answered by the discovery behind these Nobel Prizes. And to do that, I will have to summarize in a short, what is meant by standard model. And then I will spend time in really telling you why the story is still not complete. And then I will try to identify the questions which are raised by the Nobel Prize winning discoveries. And then I will sort of explain what are the questions about natures of things all around us that still remain to be answered. And then I will try to end by telling you where does particle physics go from here. All right. So the Nobel Prize Physics in 2013 was awarded jointly to two gentlemen, Francois Anglais and Peter W. Higgs, for the theoretical discovery of a mechanism that contributes to our understanding of the origin of the mass of the subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN's Large Hadron Collider. So please note, there are three parts which I have highlighted in different colors. The Nobel Prize was given to the two gentlemen who discovered the mechanism. I think I have, so here this is the picture. This photograph on the right is the photograph of these two gentlemen. Francois Anglais and Peter W. Higgs. Then this is the lecture hall on July 4, 2012, where I guess I am somewhere at the back. It was my great luck that I was giving some lectures at CERN exactly on the day this announcement was made. And here in the left photograph are the 3 + 2, 5 director generals of CERN who actually led CERN in the period when the Large Hadron Collider was conceived, built, and the experiment was performed. And as luck would have it, this person here, Fabiola Gianotti, is the current Director General of CERN, doing her second term. Now, there are various things that I want you to take home from here. That's why I've showed this photograph. And this is again this announcement happened on July 4, 2012, and this got the Nobel Prize on October 8, 2013. So now let us see. I said here already that there is something that I want you to notice, that the Nobel Prize in Physics was given to the Higgs mechanism. So it was the triumph of the theory. But please remember, in the citation that read out to you, it said it was given because it was confirmed by the discovery of the Higgs boson. That is the confirmation of the theoretical speculations by experiments. And what is interesting, and the Large Hadron Collider is explicitly mentioned. So you need theorists, you need experimentalists, and you need the accelerators. What was nice is that the experimental groups at different universities and institutes and the host of theorists all over the world had been involved in this exercise. And I'm very happy to say that there were actually also people from India, theorists as well as experimentalists, who were, and engineers who were involved in this big experiment. Even though the Nobel Prize was given for the theoretical postulation of the Higgs mechanism and the existence of the spin zero boson, that is now what we call the Higgs boson, it would have been impossible to give it without the gigantic experiments that were performed at the Large Hadron Collider at CERN and all the earlier facilities at CERN, as well as at the Fermi National Accelerator Laboratory, KEK, DAISY, along with the theoretical structure which made accurate predictions possible. So this Nobel Prize, to me, is really the triumph of collaboration among theorists, experimentalists, and the global particle physics community, and of course, this triumph of the standard model. So on that day, if you notice that picture that I showed you, everybody sitting in that hall felt it was a Nobel Prize that particle physics was getting. It was the Nobel Prize for the standard model. The second Nobel Prize was something which was given in 2015, which was given to two gentlemen. One, Professor Kajita from KEK in Japan, and Professor MacDonald, who is a Canadian but works in a laboratory. Actually, he's an American, North American, working in a laboratory in Canada. And what was that for? This is a cartoon which I quite like. This Nobel Prize was given because these two gentlemen led a very big experiment which proved that somehow, as the neutrinos are floating around in the universe, which they are all around us, and sometimes they suddenly change their character. This neutrino of the muon type or the electron type suddenly becomes a neutrino of tau type. Now, most of you know a little bit about particle physics, but even if you don't know it, I will explain it in a few minutes what is meant by these two types of neutrinos. And this Nobel Prize was given in 2015 for the discovery of neutrino oscillations, which shows that neutrinos have mass. So there are two different Nobel Prizes. And I want to now try to tell you, I have tried to give you what was the significance of each Nobel Prize. And now we will try to go back to the standard model. So I want to tell you this, that among the Nobel Prizes that are awarded for physics till to date, from the beginning, in the 25 years, out of these, in 25 years, they were given for the experimental discoveries or theoretical breakthroughs that have contributed to the standard model. and 47 scientists have got it. The first Nobel Prize for particle physics, what I call particle physics Nobel Prize, was given in 1936, and the most recent one in 2015. And many of us think that 2013 Physics Nobel was perhaps the last Nobel for the Standard Model, and 2015 Physics Nobel is perhaps the first Nobel for the Beyond Standard Model Physics. So now I think you can appreciate why I have taken these two Nobel Prizes as the which define the future directions in particle physics. So the Physics Nobel Prize of 2013, let's start about that. It celebrated the success of the standard model of the particle physics. And actually, even if we call it model, it's actually the candidate for the theory of the fundamental particles, elementary particles, and interactions among them. And it got built brick by brick over the last 70, 80 years, actually, combining information from a lot of different types of experiments and many, many innovative theoretical ideas. Now, this is the only time when I will use some technical words, but you can, if you don't follow them, you can forget them. But this is where the theorist comes in, is that one of the things that happened over these last 70, 80 years is that one realized that to describe the interactions of these elementary particles with each other, you need a mathematical framework which goes beyond quantum mechanics, and that is just given a name, quantum field theory. But not every quantum field theory is good, but only sub-quantum field theories which possess some special properties, and we call them symmetries. So, as I said, we don't need to know what quantum field theory is, so you can take that as a name. But only thing I want to tell you is that it is a mathematical framework which respects quantum mechanics and relativity. This is something every student of physics knows about. So what does quantum field theory do? For you and me, at this present moment, all we can take it is that it provides us a way of calculating processes where particles are created and annihilated. And what we call as the standard model is it's a quantum field theory description of fundamental elementary particles and the interactions among them. And this has been checked to an extremely high degree of precision because the predictions of this theory, which have been tested against data, and they will agree very, very well with the data. Let me just try to show you how well they agree. Since you are all physics students, you know something, a quantity called gyromagnetic ratio of the electron. And if you remember, even in our BSc courses, and now even in MSc we learn it even further, that the gyromagnetic ratio of the electron is almost 2. In fact, there was a very famous theoretical physicist called P.A.M. Dirac, who wrote an equation that can be satisfied by an electron which is consistent with special theory of relativity, and that's called relativistic quantum mechanics. And it actually predicts the value for a point like spin half electrons that the gyromagnetic ratio must be exactly 2. Now, quantum field theory description of electrons and photons, which is called quantum electrodynamics, this actually goes one step further and it predicts corrections to this value. And the measurement, please see in the blue that I have written, and you will notice that I have written it correct to 3 plus 2, 6 plus 2, 9 plus 12, 14 places, and out of which the error is only in the 13th and the 14th place, and that is 0.28 parts per trillion. Okay, this is measured. And what is the prediction?
मैम कौन सब्जेक्ट आपका?
Sorry?
I think someone, please mute your mic. Abhishek. Yes.
Okay.
Ma'am, your camera is tilted down, so if you can just lift it up.
Yes. At some point I wanted to see this. Thank you.
Yeah.
No, because I was getting
Yeah, now it is okay. Okay.
Yeah. So what please note that again, up to first 11, 12 digits agrees perfectly well with the measurement. So if anything, prediction is less precise than the measurement in this particular case. The prediction is 5.2 parts per trillion and measurement is 0.28 parts per trillion. So this is one particular example how well standard model works. The other example I want to give you is I show you the original signal for the Higgs boson, which was announced in that beautiful first picture that I showed you in the meeting on July 4th. And this is showing you that this particular red curve and this peak here corresponds to the Higgs to gamma-gamma signal, and this was the original signal that was seen. In fact, if I show you a plot of the signal in the Higgs to ZZ star, one Z and one virtual Z signal, then it had maybe about 100 events. And in billions of PP collisions, you have 100 or 1,000 events. And then you ask yourself a question that why is it that particle physicists immediately jump to the conclusion?
Sorry, ma'am, to disturb you. Someone else is presenting. Rashmi Kumari, please stop presenting. Okay, now ma'am, you can present.
Can I? So I have to see it again?
Yeah, you have to again present.
So I have to start presenting again. Okay.
Yes.
I'll stop sharing and then present now. Window. Share. Okay. Is that fine?
Yes, ma'am. No, it is.
Very
yes,
good.
ma'am.
Thank you. So, as I was trying to tell you that there were only a few hundred or at the most 1,000 events produced in billions of PP collisions, and there were about 100 to 500 events where 2 photons were produced, and only 10 or so events where the events had 4 electrons or muons. And how is it that the entire world jumped and said, we have found the Higgs boson, or we have found a new boson? The reason the whole world jumped up and down is because it had all the right connections with the another properties of another fundamental quark, which is the top quark. And we expected in the theory, the standard model, for the top quark mass to be related to the Higgs mass. I'm not going to go into detail, but this is just to show you how the precision with which standard model made predictions and the precision with which the measurement tested the standard model. So all I want you to do is concentrate on these green and yellow bars. These green and yellow bars tell you how accurately the masses of 2 particles, fundamental particles, W boson and the top quark were measured at in different experiments. And now I want you to focus first on this gray ellipses, and these gray ellipses were the ellipses where the W mass and the top mass should lie for measurements of properties of Z boson, which has nothing to do with things that are being presented here, but which tell you in the framework of the standard model what should be the values of MW and MT. And before the Higgs was found, so this is when we have not used any measurement from top mass measurement or the W mass measurement or the Higgs mass measurement, and then you ask yourself where should W and T lie, and this is what you find. And at that time, people said, okay, the actual measured values of the W and the top mass agree fairly well with this gray region, and therefore life is good. But once the Higgs boson was found, this blue region that you are talking about is the blue region which your measurements of the Z boson properties tell you the W and the top mass must lie if the Higgs boson mass is what was measured that day and announced on July 4, 2012. And now you see that the center of this yellow ellipse and the center of this blue ellipse lie within 1 standard deviation of each other. And I'm sure all of you are aware of the significance of this, that this told you that standard model is correct. So where did the predictions in the gray and the blue regions come from? They came from precision measurements and precision calculations of the properties of the Z boson. And I'm sure you will hear more about this, some of these things in the afternoon talk by Professor Sudhir Vempati. So what I've now told you so far, is that there is a precision theory calculation which has been tested in a precision experiment. So the discovery of the Higgs boson at the Large Hadron Collider has been the last station in the journey of the Standard Model road, which had been going on for 70 to 80 years. And the periodic table of fundamental particles and their interactions has really arrived. And this is this fundamental table of all the fundamental particles, that is the matter fermions, spin half particles, that is the leptons and the quarks. Now, I will not go through the details because I am imagining that you have a basic knowledge of what are the fundamental particles. But all I'm saying is that there are 3 generations of leptons, there are 3 generations of quarks, and notice that their masses, for the masses to be listed here, a lot of experimentation has happened. Their charges are measured, their electric charge of all these objects are measured. What I want you to notice here is that I have written here electron, but the associated object here I have written as nu L, and the masses are indeed very, very small in the somewhat wideish range, but extremely small. The mass of the top quark is 173 in some units, forget about what those units exactly are at this moment, and the mass of the neutrino in the same units is 10 to the minus 9. So there is 12 orders of magnitude in these two masses, and I want you to just note it. We will come back to it as we go along. So these neutrinos, okay? So these neutrinos are a very special thing, because here, as I told you, I have written them as nu L, nu M, and nu H. That is the lightest neutrino, middle neutrino, and heaviest neutrino. And you can see that their masses are confined to the increasing mass values range. But you will sometimes see also the 3 generations of particles written in the following fashion, where associated with an electron, you write a nu E. What does that mean? That when there is an electron neutrino incident on some particle, and say a proton or neutron, then it produces an electron. Whereas a nu mu, when incident on a nucleus, proton, neutron, or what have you, produces a muon, and nu tau produces a tau minus. If I'm left with time, I will show you the actual photographs which found neutrinos in this fashion. But right now, all I'm saying is that each electron has its own neutrino. And why is it that here they are written as nu E, nu mu, nu tau, and here they are written as nu L, nu M, and nu H? This is the result of the discovery which was made by Kajita and MacDonald, and for which they got the Nobel Prize. So we will come back to this as when we discuss the Nobel Prize. Right now, I am just completing my discussion of standard model. So the standard model has these fundamental building blocks. The up quark, 2 up quarks, and 1 down quark will make a proton. And charm, strange, top, and bottom actually do not appear anywhere in normal matter. They are created and also decay in the high energy collisions, but their existence is very well known, because we have seen bound states of these charm, strange quarks, or the bottom quarks, and a lot of experimentation goes on today to understand the mysteries of the standard model even further by studying those bound states. But that's a different story, a different talk for another day, and we don't worry about it. All right. So there are 4, these are fundamental particles. Then there are 3 fundamental interactions. One is the electromagnetic force, which we all know very well, and that's described by the quantum field theory, which describes it. It's called quantum electrodynamics, and I will use the word QED. Then there is the weak force, which causes the radioactive decays as well as the energy generation in the sun. And these two together are described by something called the unified electroweak theory, or the quantum electroweak theory, quantum flavor dynamics, and that is the one where the all-important and well-known ubiquitous Higgs boson plays some part. Then there is strong force, which is responsible for forming the bound states of quarks and gluons into protons and have protons and neutrons bind together to form nuclei, and that's called quantum chromodynamics, QCD. And the oldest force known, gravitation, however, we do not have a quantum description, and I will leave it at that. I will not discuss this particular interaction, but the remaining three interactions, and what is important is that what we have understood over the 20th century is that these three fundamental interactions are also mediated by fundamental particles. The electromagnetic interactions are mediated by photons. Then W plus W minus and Z0 mediate weak interactions. Then there is gluon, which mediates strong interactions. And the table of the integral spin particles is not complete. And this particular entry was added on 4th July 2012. And this is the sense in which discovery of the Higgs boson completed the periodic table of particle physics. So now what is the point? The important point in all this is that, please note here, the photon has zero mass. Gluon has zero mass. This has been tested, okay? I told you that these numbers are not, the fact that these numbers are written there means that experiments have been performed, and they measure the value to this, whatever is written here. Whereas W plus W minus and Z0, whose discoveries themselves got quite a few Nobel Prizes, have masses which are much, much bigger than zero. Not only that, they are actually comparable to the mass of the top quark here, for example, which is 173, and mass of a W boson. Now my computer is frozen. Okay, 1 second. Yeah. The mass of the W and the Z boson is like 80 to 91, and mass of the Higgs boson is 125. Okay. So all the electroweak gauge bosons and all the fermions are massive. But now the problem is that the high precision predictions that I told you, in this plot, which I showed you, I will bring that plot, which I made in this particular, that people made in this particular plot, this high precision measurement indeed cannot be made if the fermions and the gauge bosons are massive. Why? Because the predictions can be made only when the laws of motion, which are obtained from the corresponding quantum field theory, show certain regularities, which I call symmetries. The fact that predictions agree with measurements tell us that the laws of motion must have those symmetries. But our naive knowledge tells us that if the particles have masses, those symmetries are broken. So how do you have your cake and eat it too? You know that this fact that the predictions agree with measurement means that the theory has the symmetry. And indeed, this is what was told to us by Higgs. And that is why Higgs and Anglais got the Nobel Prize. Because the Higgs mechanism actually provided a way to have the cake and eat it as well. And it normally said, and I will try to explain that in the next 2 slides, it is normally said that the Higgs boson gives mass to the matter particles. Okay, now what does it mean? What is meant by that? Let me try to explain that in a very simple language. And for that, we need to know one very small thing that's called handedness. So let's consider a spin half particle with its spin pointing along the z-axis, and the particle is also moving along the z-axis. Now, such a thing is called the right-handed state of this spin half particle. If the particle is massive, then I think all of you will see that I can keep on making Lorentz transformation, so that actually I will go to a frame where the particle is at rest. I can continue making Lorentz transformation such that the particle will start moving in the opposite direction with respect to that Lorentz frame. So you will see that you can actually make a transformation from a right-handed state to a left-handed state via Lorentz transformation if the particle is massive. Now, experimentally, it is known that the weak interactions treat left-handed fermions and right-handed fermions differently. So now this is a real problem, that there are these particles which deal with left-handed and right-handed fermions in a different manner. And on the other hand, if the particles have masses, then the theory, as for massive particles, we should not be able to transfer a left-handed state into a right-handed state. So that is really the question now. And therefore, we have to try to understand it. I'm sorry, my phone rang and therefore I lost my chain of thought. Let me repeat what I'm trying to say, is that the weak interaction, many of you have learned this, that the neutrinos that are emitted in beta decay are left-handed. Now, if the particles are massless, there is no problem, because left-handed, and you cannot convert a left-handed state into a right-handed state, and laws of motion treat left and right differently. But if it's a massive object, we just now understood that we can go from one Lorentz frame to another Lorentz frame, and a right-handed object will convert itself into a left-handed object. So now you ask yourself a question, what is meant by this, that the electrons that are emitted in the beta decay are left-handed? How can that be? Because I can go to a different Lorentz frame since they are massive, and then there is a problem. So Higgs mechanism provided a way to allow left-handed fermions to change their handedness, and hence that removed the differential treatment of a fermion with two-handedness and made it compatible with special theory of relativity, even if weak interactions produce only left-handed electrons. So this is really the origin of the statement that the Higgs boson gives masses to all the matter particles. What it means is that Higgs boson explains how all the matter particles can have a non-zero mass and still be consistent with special theory of relativity. Okay, so this is the point. It says that the Higgs mechanism shows us how the interaction of matter fermions make the existence of a non-zero mass consistent with different symmetries. At this point, I will also tell you that the standard model contains only left-handed neutrinos, and this would make sense only if they are massless in the standard model. Now, there are actually much more has happened in the 10 years. Obviously, much more has to happen. And in the 10 years since the discovery of the Higgs, one has been able to measure the strength of the interaction of the matter particles with the Higgs boson. And the basic prediction of the Higgs mechanism is that the mass is proportional to the strength of the coupling. And indeed, these measurements, and recently even this measurement for the muon has been made. And indeed, the line really, the muon measurement also lies on this line here. And therefore, it's an absolute triumph that over 4 orders of magnitude of the masses, the couplings of the particles with the Higgs boson are proportional to the mass. So indeed, Higgs explains the mass of all the fundamental particles that we have seen so far. And Nobel Prize was given because of 2 reasons. One written in blue here, that the Higgs boson was observed, predicted with the properties which are predicted by the standard model, this slide here, and with the mass value which was predicted from the precision measurement. And for that, I already showed you this slide here. Okay, so this slide and this slide are the 2 measurements which justify the Nobel Prize for the Higgs mechanism. And this really proved to us that SM is the right description of the 3 interactions among elementary particles, and which are mediated by force carriers, which are gauge bosons. So the question that was answered is that how can all the particles have non-zero masses, and at the same time, the processes such as the nuclear beta decay remain unchanged in different frames of references in relative motion with each other. So this was the question that the Higgs discovery really answered. So now you can ask a question. So is the story over? This is such a great fact. Far from it. And why? Is it just because we like to keep ourselves busy? Actually, not quite. Even before the Higgs boson was discovered, particle physicists knew that the standard model is not a complete theory. And the reason for expecting things beyond the standard model, that is new interactions and new particles outside the standard model. This reason got reinforced by the discovery of what we call a light Higgs boson. So what happened was that one had designed the Large Hadron Collider to find the Higgs. At that time, one had actually hoped to find more things. I will explain these, So when in 1986, when the Large Hadron Collider was being discussed, and property, what its capabilities should be, these kinds of things were being discussed, people thought, as physicists like me, thought that when we reach the Large Hadron Collider, just on the horizon, we will find the Higgs, we will find an understanding of what is called the dark matter, what is the baryon asymmetry in the universe. We thought we are going to be able to climb all these big mountains in the Alps, which is where the Large Hadron Collider is. And finally, having reached at the peak of the Higgs boson, now people have realized that from a distance, these three looked to be very close to each other. Now we realize that there are still peaks to climb and questions to answer. And that is why we think this is not the end. That is why we think there is physics beyond the standard model. So let me begin with what are the different reasons. One is that the Higgs boson seems to have a mass which is comparable to the W and the Z bosons. I pointed it out to you. Higgs boson has a mass of 125 GeV, and the W and the Z bosons have masses of 84 and 92 GeV. In particle physics parlance, therefore, we say that Higgs is a light particle. And why? Because in a quantum field theory of spin zero particles, quantum effects allow, in fact, the mass of the Higgs to be as large as possible. That means the largest mass in the theory. So this does not happen for gauge bosons and fermions. So theoretically, we understand why the W and the Z are light, or why the fermion, like a top quark, is still light. That is, they are all of the same order of magnitude. But we do not understand theoretically why the Higgs mass also lies in the same range. Therefore, we would like to explain theoretically why the Higgs boson is light. And this led to a lot of different theoretical ideas which introduced particles and interactions beyond the standard model. So we have theoretical challenges. We would like to understand the mass of the Higgs itself. That's what I wrote here. What controls the mass of the Higgs? We would like to understand the large hierarchy of the observed masses. For example, I already pointed out to you that the ratio of top quark mass to the neutrino of electron type ratio is 10 to the 12. Top quark mass to the electron mass is 10 to the 6. MT to MW is 2, and MT to MH is 1. And this is something, these are all mass problems. For example, we don't even understand what is the proton mass, because proton is made up of 2 up quarks and 1 down quark. But the mass of the proton, which is 1000 MeV or 1 GeV, is actually much bigger than the sum of the 2 up quark masses and the down quark masses. And frankly, even when we say that the Higgs boson explains mass of everything around us, it is true only at the level of quarks and leptons. The mass of the proton, and hence the mass of all of us, is
R is nothing but universal gas constant. Okay, nama ideal gas constant ante manaki ideal gas Cp minus C is equals to R. Manku inkote
Raghavendra
anedi moles there.
Hello, Mr. Raghavendra.
Gamma ante enti? What is gamma?
Raghavendra.
Maybe Rajesh, I think you can mute it because you have the privilege.
Gamma is the ratio of specific heat capacity is at a constant pressure, and ratio of specific heat at constant water.
Excuse me. I am muted. Okay. Can I go on?
Yes, ma'am.
Yeah. Yes, ma'am. All right. So now, having told you what is the significance of Nobel Prize of 2012, what is the significance of the fact that this Nobel Prize tested the standard model, what is meant by standard model, and what are the questions that were answered by the Nobel Prize of 2012. Now I go to the next stop that I told you about, namely the Nobel Prize of 2015. Neutrinos oscillate. So what are neutrino oscillations, and what does it mean that neutrinos are mass? So I told you that there are 3 types of charged leptons and there are 3 types of neutrinos: nu e, nu mu, and nu tau. Each lepton has its neutrino. But actually neutrinos are very, very loyal. That means that interacting with matter, a neutrino of one type X will produce a lepton X. That is, nu E will produce electron, nu mu will produce muon, nu tau will produce tau. But the funny part is neutrinos are pretty political, that all the neutrinos that we have observed are left-handed. And that is actually a bit of a problem, because if the neutrinos are massive, then you have to wonder, that it is as long as neutrinos are massless, they can be left-handed only, and there is no problem in the world. But as I explained to you, when particles have mass, we can convert a left-handed state into a right-handed state by simply going to a different Lorentz frame, and therefore things become very different. Anyway, so now we say that, this is sort of joking descriptions, that neutrinos are very friendly. That means they mix. Now, what is meant by mixing? Let's try to understand. So what happened, and I want to explain this in very simple words. Neutrinos coming from the sun were detected. Sun produces energy and light, everything through nuclear reactions. I'm sure all of us know that at the center of the sun, there is a fusion process that is happening, and through the fusion process, energy is created, and at the same time, neutrinos are emitted. Now, these neutrinos which are emitted from the sun are actually neutrinos of electron type. And these neutrinos are actually closely tied to the amount of the energy that is produced by the sun. It is actually predicted extremely well. So when they arrive at Earth, they should actually produce electrons, because it is the nu E which were produced in nuclear interactions. And I told you neutrinos are very loyal. But however, the number of detected electrons did not match with that expectation. So what has happened? Theory can predict how many neutrinos should be produced in the sun, because that is tied to the energy of the amount of energy that is produced in each nuclear reaction. As a result of which, we know what is the number of neutrinos that are arriving on the Earth, but the number of electrons that are produced do not match with the number of neutrinos that we think should have been produced inside the sun. Which means that the neutrinos which started their life in the sun as an electron neutrino, in fact changes into a neutrino of tau type or neutrino of muon type by the time they arrived on the Earth. And the experiments that Kajita and McDonald did actually counted how many taus and how many mu's were produced, along with how many electrons were produced in the big experiment that was conducted to detect the neutrinos which were coming from the sun, and they really proved that the neutrinos changed their character. Now, what is meant by this oscillation? Actually, we are very used to another type of oscillation, so I will take that. We know light oscillates. Let's consider plane polarized light. So, and let's also consider circularly polarized light. So let me denote the plane polarized light by X and Y, and circularly polarized light by L and R. So as we know, and this is something that all of us know, that L and R are different linear combinations of X and Y. So are X and Y linear combinations of L and R. Because a right-handed circularly polarized light is nothing but polarized light in the X direction plus polarized light in the Y direction, and equally added in the amplitude. And the left is again a linear combination of X and Y, a different linear combination. So a polarizer, as you know, treats L and R lights with left circularly polarized light and right circularly polarized light differently. That means that even if you had a light which was unpolarized, that means it had equal amount of left and right circular polarized light. It was plane polarized light, let's say, in a particular plane of polarization. Then the polarizer actually splits it and changes the degree of polarization. And therefore, a given linear combination of X and Y will emerge as a different linear combination of X and Y after it passes through the polarizer. And that is what we call as a rotation of plane of polarization. So we know this very well in case of light, that light oscillates between 2 degrees of polarization, as it were. It converts itself from one state of polarization to another state of polarization when it interacts with a polarizer. For neutrinos, vacuum itself is a polarizer. Vacuum itself, you can call the vacuum to be a polarization. But then what is the distinguishing feature? In this case, I told you the distinguishing feature was one was left polarized, one was right polarized. In the case of neutrinos, it is the mass. Let me consider only the state two flavor case. Now, what is meant by, just like, for example, when I take a plane polarized light, it is neither right circularly polarized nor left circularly polarized. Similarly, when I take a electron neutrino beam or a muon neutrino beam, they by themselves don't have a definite mass, but a linear combination of the two with some mixing angle has a definite mass. Let me call them nu h or nu l. So nu mu, for example, is a linear combination of nu h and nu l, and nu e is a linear combination of nu h and nu l. Nu h and nu h has the particle which is heavier, has a fixed mass mh, and nu l is a lower mass particle mu l. And just like here, this is just like here, okay? I am expressing these are the interaction eigenstates. This guy, when it interacts with matter, will produce a muon. This guy, when it interacts with matter, will produce an electron. So these are interaction eigenstates, and these interaction eigenstates are written as a linear combination of the mass eigenstates. And the different masses mean that for a given energy, they will have different speeds, clearly, right? Because E is equal to P square by 2m, and speed is P by m, at least non-relativistically. So at birth, when you produce a muon, because a muon is, nu mu is produced, let's say in a muon decay. So nu mu, I wrote to you, is a linear combination of the heavier guy and the lighter guy, doesn't have a fixed mass itself, and then it starts traveling. Now, when you start traveling, your mass makes an effect, and the heavier component lags behind, the lighter component goes faster, and therefore, when you come and look at that neutrino a certain distance away from the place where it was born, and now you look at this point. At this point, the strength of nu h and nu l are different than the strength of nu h and nu l at this point, and therefore, the strength of nu h and nu l being different, I can now write down that something which started its life as nu mu and had nu h and nu l in certain proportions, these proportions get changed, and therefore what happens is that even though here we had only nu mu, here we have both nu mu and nu e. That is how a nu mu has oscillated into a nu e. And if you have a detector here, the detector, the nu mu interacting with the detector will produce a muon, and the electron, you will still see also some electrons being produced at this place, and that will tell you that a nu mu has changed its character. Some part nu mu's have changed themselves into nu e. So it looks a little bit like this. These are the neutrino oscillations. Now I have changed the notation slightly in the figure. Nu h is nu2 and nu l is nu1 in this figure, but that's just a notation. And now you see nu2, which was the nu h, lags behind. Nu1 moves faster and faster. So you start, this guy starts its life as nu mu. After a certain time, depending on the wavelength of the oscillation, at this point, it has all got converted into nu u. At a further distance, when the full range of oscillation is complete, it has come back to being a nu mu. So these are the neutrino oscillations. And now, this is what Tajita and McDonald's experiments, or the experiments done by the team, which was led by them and which had these immensely big detectors and immensely complicated engineering, actually proved. Okay. Now, standard model contains only left-handed neutrinos. I already talked to you about this, that oscillations mean mass, but because that's what these oscillations are telling you, that they are non-zero masses. But if they have non-zero masses, then how do we, what happens to the right-handed neutrino? They must be there, they're non-zero masses. But in the standard model, the right-handed neutrinos, nobody talks. It's like a shunned object, you know. Nobody talks to them. The only particle that can talk to the right-handed neutrino is a left-handed neutrino. And they can talk to each other only if they have non-zero mass. And experimenters tell us that neutrinos mix, and therefore the only way they can talk to each other is through the mass term, and therefore they must have mass. That is why you notice that the Nobel Prize citation said that they discovered neutrino oscillations and hence proved that the neutrinos must have masses. All right. So you will say, so what? All right, you have told us about truths of few fundamental laws of interactions between fundamental particles. Seems very interesting. These neutrinos like to change their character into one another. So what? Why is this important to us? What is the reason why this is important to all of us is because these laws of particle physics, which we have found to be functioning at distance scales of Fermis and smaller, they seem to be of relevance in addressing things that happen on cosmological time scale, that is at the beginning of the universe, or astronomical distance scales, that is millions of megaparsecs and above. I mean, how was everything formed? How did the nucleons form? How did the neutrons and protons form? How did the neutrons and protons come together to form a nucleus? Can we explain the relative amount of, lithium, helium, hydrogen, oxygen relative to each other? Are there any reasons? And how did the stars and galaxies form? Of course, to answer these questions, you need a lot of knowledge of astrophysics, the classical physics, but you also need knowledge of nuclear physics and particle physics. And to understand these things, you have to have knowledge of how fundamental particles interact with each other at the fundamental level. So in answering these questions, the known physics of the Standard Model plays an extremely important and unavoidable role. You have to use the knowledge that comes from here. And I already gave you an example of neutrino oscillations for that. Because, for example, if we don't have this neutrino oscillation as an example, then we would have to go back and say that our understanding of how energy is generated in the sun is wrong. Now, by understanding neutrino oscillations, we have understood that our understanding of the generation of energy in the star is completely correct, which means that our knowledge of Standard Model of particle physics and its extensions have helped us understand that our understanding of how stars are formed and how stars evolve and how stars create energy is all correct. So therefore, that tells you the simplest connection of the laws of particle and nuclear physics with the more fundamental things that might have happened, as I said, in the universe and the cosmological timescales or astronomical distance scales. And therefore, there are many reasons. Okay, I will tell you now different reasons for the BSM, and some of the observational reasons actually come from what I call cosmic connections. There are, for example, the basic features of the three fundamental interactions that I talk so much about actually has a bearing on issues which are cosmological. As it happens, the contents of our periodic table account for only 5% of the matter in the universe. When you look at the energy budget in the universe, only 5% is made up of the particles which I showed you in the periodic table. And astrophysical evidence is really very, very convincing. And astrophysical evidence tells us that at least 26.8% is actually made up of matter which is not seen by light, which does not interact with light, which does not shine. And now we know that this dark matter has to be made up of a particle which is not present in the particle data. It is not present in our periodic table. But we are able to draw this conclusion only because we have understood the interactions of all the Standard Model particles. Okay. Then there is a 68.3%, which is dark energy, which we understand even less. But right now, this dark matter and the dark energy are two big puzzles, and dark matter is a puzzle which perhaps particle physics may have, or physics beyond Standard Model may have a handle, may provide a handle on this particular point. How good is the evidence for the dark matter? The evidence for the dark matter is pretty convincing, and that has to do with the fact that you measure velocities of rotation. For example, here this is galaxy M33. It rotates around the center, some center, and when you notice the rotational velocity, if the visible mass was all that existed, the rotation speed of the galaxy as you go away from the center in light years, by the way, that is even 1 light year is the distance that the light travels in 1 year. If there was only the visible matter that we see, then the velocity should have decreased as you go further and further out. And that is something very easily understood. You can do that small exercise in your classical mechanics class and understand that as you go further and further away, then the velocities of the objects should reduce. But what you find experimentally is that the velocities do not go down. Velocities remain flat. And this on the left, I have shown you the rotational curve, which was first measured for galaxy M31 in 1970 by the great astronomer Vera Rubin. And you see that her measurements were pretty good. Now, of course, we have evolved and we have got a much better measurement. So this thing that the rotational velocities move like this tell us that the dark matter really exists. Actually, there are some more measurements of dark matter. And one is, for example, by looking at the cosmic microwave background radiation and the anisotropy in it, which was measured by the experiment called Planck, as well as observing collisions of galaxies. And here, for example, in blue is the mass that is tracked by gravitational lensing experiments, and in red is the mass that is tracked by X-ray emissions. And then one sees that the mass that interacts with light is less than the mass that does not interact with light, because this is the one that is seen only in gravitational lensing. So this is one of the proofs that dark matter exists. So this is one puzzle that we have. Second is, why do we exist? What is meant by that? Early universe in principle had equal amount of matter and antimatter. But universe of today seems to have a matter and antimatter asymmetry. An explanation of this asymmetry in the universe in terms of the known properties of the standard model particles, and that this is called CP violation, that is asymmetry between matter and antimatter. This is measured in laboratory, and standard model particles have this property, have this asymmetry, and the explanation of the matter-antimatter asymmetry that we have seen in the universe in terms of the measured asymmetry that is measured in the laboratory is actually possible. And just to give you an idea, the difference between NB, the ratio of photons, baryons to photons, and ratio of antibaryons to photons, one sees that in the early universe, everything was only photons. In today's universe, and baryons and antibaryons were equal in number at that time. And then now, in today's universe, the baryons are less than the photons, but still they are much bigger than the number of the antibaryons. And a quantitative understanding of this number, we can calculate this number. Qualitatively, we understand in the laws of standard model why this happens. But to explain it, apart from what one finds quantitatively to get the answer correct, we can get the answer that this should be NB over N gamma, should be of the order of 10 to the minus 10. But to get the exact answer, 6.1 into 10 to the minus 10, you actually need physics beyond the standard model. And this beyond standard model physics is something that is a matter of great interest to particle physicists and cosmologists and astrophysicists all alike. So this is what I meant by saying that this is not just for particle physicists, this is for our ability, our aim, our desire to understand mysteries of the nature. So there are various observational reasons. I have tried to tell you a few, and I will list them here. One is the dark matter makes up about 27% of the universe. Then I also told you there is direct evidence for non-zero neutrino masses, and I tried to remind you that in the standard model, neutrinos are massless. Then we do not have a quantitative explanation of the baryon asymmetry in the universe, matter-antimatter antisymmetry in the universe. Then we do not have we have found a light Higgs boson, and we do not know what keeps the Higgs boson light. Then we have observed a cosmic acceleration, and that is the dark energy. But at present, I think particle physics has really no insight in dark energy. It is more the theories of gravitation, which I have left out of my talk right now, which have some bearing on this question. And that is the thing, we feel the force of gravity, but we do not have a quantum description. So these are the reasons for continuing our theoretical and experimental explorations. And in all this, the mass seems to play a very important role. Just like the massive gauge bosons, massive fermions led us to the idea of Higgs boson, led us to realize the theories which predicted how to do exact calculations. It is the same mass issue that's now pushing the boundaries of knowledge further and further. So the question is, why do neutrinos have such tiny masses? Do we understand why some particles are heavy and some are light? Why is there dark matter? What is the dark matter? And what is this dark mass in the universe coming from? Because it is not coming from any standard model particle. The mass of the protons, I already told you, it does not come from the Higgs mechanism. It's much, much bigger, 1,000 times bigger than the sum of the 3 quark masses. Why does that happen? This is actually $1 million question that has been put forward by something called Clay Foundation. So Clay Foundation in New York has actually said that they would offer $1 million to the person who provides an answer to this question. Then there is a question, is there a graviton? I wrote about photon, W boson, and I kept on telling you that associated with each interaction, there was a boson. So how do we write a theory of a graviton? It took us a very long time to go from electromagnetism and the various Ampere's and Faraday's laws to come to the idea of photons, where we came thanks to Einstein. But for the gravitons, we still have a ways to go. We are beginning to see gravitational waves, but theoretical explorations in this front are still something that we have to do. The quantum structure of gravity and the space-time. The future is in understanding the rest of the mass of the proton, that is in non-perturbative quantum chromodynamics and lattice calculation. Future is in the high energy, higher luminosity Large Hadron Collider, about which you will keep on hearing in the next 4 or 5 days. And the data will show us the pointers for physics beyond the standard model. As many of you know or should know, is that India is now an associate member at CERN. We also have theoretical groups which are working on how to extract beyond standard model physics from the experiments that will be performed in the high energy and the higher luminosity LHC. Future is in the joint studies of the big and the small, and that's in the experiment with neutrinos. In fact, Indian Neutrino Observatory, which has unfortunately been stalled, is one such big experiment that India is planning, and I'm hoping that some of you will actually participate and will be able to contribute to the physics of the next decade of the neutrinos at the world level. Then, as I told you, there is this unity between particle physics and astrophysics and astronomy and cosmology and what have you. And a new window in this astronomy has been opened by gravitational wave detection. That is the LIGO, that is the Laser Interferometry Gravitational Observatory. And as many of you might know, there will be LIGO India, which is supposed to go in action in 2025. Then there are experiments with high energy photons, which are coming from galaxies, from beyond. And there is this big experiments, one of them called Square Kilometer Array, which is being set up in South Africa, where India has been invited to participate, partially because of an excellent experiment that runs near Pune in GMRT, Giant Meter Radio Wave Telescope. And now, therefore, India would be participating in newer and bigger radio telescopes. And there are lots of very important and interesting experiments that your generation can do, can participate, and future looks very bright and inviting. So I guess I stop here and I'm open to questions.
Thank you, ma'am. Am I audible? Hello. Yes, Rajesh.
Yeah, okay.
Yeah,
So
thank you.
Godbole for this enlightening talk on particle physics in such a beautiful way. I had the privilege to meet you in person at IIT Guwahati in Feb 2019, and I also thank the internet for once again blessing me with you with the remarkable aura, motivation, and in-depth knowledge. So before proceeding for the questions, the participants were asking about the soft copy presentation. Can
you actually, it might be easier if you people type the questions, because I'm not able to hear the question. Or maybe
am I audible, ma'am? I'm just
you are audible, but you are breaking off now and then. Hello, you are breaking off now and then. So
okay, let me.
Now you're better. Go ahead. Speak.
Let me try again. Yes, let me start again. Thank you, Professor Godbole, for this enlightening talk on particle physics in such a beautiful way. I had the privilege to meet you in person at IIT Guwahati in Web 2019, and I thank the internet for once again blessing me with your remarkable aura, motivation, and in-depth knowledge. So, before proceeding for the question, yes, I am audible?
Yeah, you are audible. Go ahead.
The participants were asking about the soft copy of presentation. Can they get it?
Sure. I will send a Google Drive link to Dr. Daya, and then you can choose a site to put that soft copy on. Okay? So that's no problem at all. That's no problem at all.
Yeah. So now moving towards the question, there are so many questions from the participant, but let me randomly pick 4 to 5. The first question is from Anubhav Garg. He's asking about how Nobel Prize helps scientists for their monetary agenda.
I think I'm not sure I would like to answer this question, but I will. It's not a question of monetary.
So 3 kBT, right? And with the Avogadro number. That is mu is equals to 3R. Delta Q is equals to delta.
Please mute the participants.
Yes, please. Second relation. Delta Q is equals to delta U plus PdV. A first law. Delta Q is equals to delta Q.
Sorry, I can find it.
That is delta Q is equals to delta U is the first law. dq is equals to.
You can remove Raghavendra is there.
Yes, I am trying actually.
Okay. Yeah, it's muted now.
Okay.
Yeah.
Okay. Okay, ma'am. Go ahead, please.
I am not very happy with this question. Actually, I would say this clearly, because I think it's not the monetary advantage of the Nobel Prize that one is talking about. The importance of the Nobel Prize is in the acceptance or the contribution to our fundamental knowledge that the person's work has made. Okay, I mean the monetary remuneration is incidental. Okay, so I would like you to appreciate this, that the value of the Nobel Prize is not in the money. The value of the Nobel Prize is in the recognition of the very fundamental advancement of knowledge that scientist's work has brought about. Okay, so that's my very short answer to this question. Okay.
Yes, ma'am. Thank you. The next question is from Raghav Sa. How is the spin gyromagnetic value measured in the experiments?
Oh, it's just measured by looking at the precession of the spin of the muon. In fact, this is G-2 of the muon, and you can actually go and look in do a Google. You will find there is a very precise measurement of how the spin of the muon precesses when it is moving in a circular motion. Okay, and that is decided by the gyromagnetic ratio.
Okay, thank you, ma'am. I hope the answer is clear to the participant. And next question is, ma'am, is there any application for the neutrinos property in quantum computing and information?
Actually, none. Not that I know of. Okay, but I don't know. Someday, because I don't believe so. I know that it's the photons which one can use quite effectively, single photons, but I have not known of anything where neutrinos can be used for quantum computing and information.
Okay, thanks, ma'am. Okay, the next question is from Maria Plakatu. What experiment or theoretical problem made the scientist to think about dark matter and energy? Energy.
No, those are good questions. The dark matter, as I tried to explain to you, but anyway, given the time, I didn't, this was not a talk on dark matter. So let me try to tell you quickly. The point is that think of an object which is rotating about a center of mass, okay? And you can calculate the speed with which what is the rotational speed. That you can do by using just the fact that it's using Newton's laws of motion and the circular motion. Now, as you go away, when a particle is moving at a distance away, more and more away from the center of the mass, you expect that you can calculate and you can see that the velocity, rotational speed will reduce. Okay, that's a simple calculation that you can do. Now what happened, and this was first noticed in 1930 by an experiment by Babcock and Zwicky, astrophysicist Zwicky also noticed it. And what they noticed is that in the galaxy clusters, what they did is that they found that the velocities do not seem to quite reduce as you go away from the center. And actually, they didn't quite measure rotational speeds. They simply measured speeds of different galaxies and galaxy clusters. And then they treated it like the gas law. Okay. And then you said that, can I calculate using virial theorem and using the energy, can I calculate the velocity? And then you found that the velocity of the objects in the clusters differed. Differed substantially in different galaxy clusters, and which essentially said that whereas the two galaxy clusters had the same masses, same visible mass, but the velocities differed. So which in turn led him to postulate that the places and the galaxy clusters where the velocities are higher must be orbiting about a larger mass, because larger the mass around which things are orbiting and moving, the velocities will be larger. And the second experiment which was done by Vera Rubin, which was in 1970, where she actually showed, and I showed you that graph, that as the distance from the center changed, the galaxy's velocity, rotational speed remained constant, whereas if the visible mass that is inside was all that was concerned, then the velocity should have decreased. I'm sure you're familiar with Coulomb's law, that if there is a fixed amount of charge and you keep on, cover it with a bigger and bigger sphere and ask the question how a particle moving at a farther and farther distances moves, with what speed it moves, as long as the charge is fixed, the velocity will reduce as you go further and further away from the charge. But here, if the velocity does not reduce as you go further and further away from the mass, that means that there is more mass that is getting included in your path of the particle that's moving around, and that's why the velocities don't quite damp off. And that is the evidence that there is mass inside this around which these galaxies are rotating, and that mass is not something that you are able to see. It's not visible, it's not stars. That is the answer. At least that is one reason for the dark matter. Other experiment for dark matter, which I showed you, for example, was this bullet cluster collisions. In these bullet cluster collisions, they measured the mass that the clusters galaxy clusters collided. Then they measured the mass by two different methods. One method was to measure the mass by gravitational lensing, and that was what was denoted by the yellow blob, blue blob. And the red blob was something that you measured the mass from the X-ray emissions. The X-ray emissions means that that's a visible mass. That's mass which interacts with matter. That's a baryonic mass. And what one found is that the galaxy clusters have a baryonic mass, which is the red area, but the actual mass, the gravitational mass which has gravitational interaction, extends far beyond that red area, and that was that blue region. So that's an impact, sort of irrefutable proof that dark matter exists. And last but not the least is the anisotropies in the cosmic microwave background radiation. expansion. And these anisotropies that are measured are actually as a result of the role that the dark matter does in the provides in the structure formation of the galaxies. And that's a much more complicated issue, and which I cannot just explain by waving my hands. Okay, so have I answered the question about how do we see dark matter? And dark energy is an entirely different beast. That has to do with the fact that we are finding that, that we know the universe is expanding. And the expansion of the universe, the rate of the expansion is also increasing. That means the universe is accelerating. And this acceleration of the universe cannot be...
Manisha, you can remove the participant.
All right. So I hope people have understood my answer about dark energy also. Okay.
Yes, ma'am. Thank you so much. The next question is same from Maria Plepetu. That is, what experiment or theoretical problem, can we associate entropy to photons as we do for the particles?
Yes, we can.
Okay. And the next question is from Shreyan Goswami. To measure the rotational velocity of the galaxy, one needs light, right? But dark matter does not interact with light. Then how does the rotational velocity being equal depict dark matter?
Okay. The rotational velocity has nothing to do with light. Rotational velocities have to do with a gravitational a mass rotating around another mass. Okay? One mass rotating around another mass. And you're measuring the velocity of that mass. And what you find that as you go away from the center, the velocity of that galaxy, the galaxies which lie further away should actually, the parts which lie further away from the center should rotate slowly. And then you find that do not rotate slowly, but their velocity remains the same. And that in turn tells you that the gravitational, there is something else which provides the gravitational force which keeps the velocity of the rotating objects at the higher level. When I'm talking about using Newton's laws of motion, I'm simply talking about two objects which interact with each other through gravitational interaction. Write down that the gravitational force is G, Newton's constant, times m1 into m2 by r. That is the potential. And equate it with the kinetic energy, which is 1/2 m r square omega square. Solve this equation. G m1 m2 by r equal to 1/2 m1 r square omega square. Okay, m1 is the mass of the guy that is moving around. And then what you find is that if m2, for a fixed value of m2, as the distance increases, the velocity should decrease. If the velocity does not decrease, that means that the m2 keeps on changing as you change r. And that m2 is the mass around which m1 is rotating. Is this clear?
I hope the answer is clear to the participant. If
is it clear to you?
Yes, yeah, it is clear. In the chat box, they said yes.
Yeah.
Okay, let's move to the next question. The question is from Varsha Tyagi. For someone who wants to carry out research in cosmology, how much would you recommend diving deep into the knowledge of particle physics?
For somebody who wants to do cosmology, I think it's actually extremely helpful to have a basic knowledge of particle physics, because I'll give you an example. Okay, there is an example that nowadays, of course, we are beginning to think about very deep cosmological questions, and early universe, the inflationary theories, for example, calculation of relic density of the objects which are left from the point of early inflation. And when you want to understand that, you need to understand the basic fundamental particles which were created in the early universe by interaction with the radiation, and the relic density got decided by how these particles interact with each other. So For example, and even further, when, for example, you look at properties of neutrinos, how do neutrinos behave? In the very early universe, when what is called, when you can think of a period when the space-time was, you had to consider the curved space-time. That is, the gravitational interactions were so strong that you have to think of curved space-time. Even the properties of neutrinos sometimes are very minutely modified, and they can affect, for example, the evolution of the universe, of the early particle densities, different types of densities of different particles as we observe them today. So indeed, I think it will be very, very useful for a cosmologist of the day to have a basic understanding of particle physics, because then when you go and try to understand gravitation, the whole idea is that theoretical framework which you are using to understand the particle interactions is presumably going to be someday, you're going to find it to be the same. So my advice is, yes, indeed, you have to look at it. Okay?
Yes, ma'am. Thank you. I hope the answer is clear to the participant. So the next question is from Simran Kaur, and she's asking, can you explain how the anisotropy of CMBR is related to dark energy?
Anisotropy of CMBR is not related to dark energy. I repeat it again. The anisotropy of CMBR is related to dark matter. Okay? And that, as I told you, what happens is that when the structure formation of the earliest galaxies are forming, dark matter provides the seed, the things which we have gravitational attraction, it provides the potential well in which the matter falls and forms a star to begin with. And the stars from galaxies. Okay? So dark matter is relevant for anisotropy of CMBR. But dark energy is inferred from continued acceleration, that our universe is accelerating, not just expanding, but the speed of expansion is increasing. And that has to do with solving the Friedman equations of motion. Okay? So dark energy is a very different beast, and dark matter is a different beast.
Yes. There is another question related to this one, I guess. Is there any relationship between cosmic inflation and dark matter?
Inflation and dark matter are not related. Inflation and dark energy, theories of inflation and dark energy are related. Okay?
Yes. There are so many other questions right now, but I think we should move on with the session. So let me thank the professor again for such an enlightening talk. And before moving further,
I will actually make one offer. If people want, they can write to me questions in email. I will try to answer them.
Yes, sir. That will be very nice. Thank you.
Dr. Daya can share my email ID, my Gmail email ID. And
yeah, you can. Sure.
Okay.
Yeah.
Because I can see there are a large number of questions, and I know that some are repeated, but some are not. So I'll be quite happy to answer by email. Okay, because there are some very good questions. Somebody has asked why is neutrino not dark matter? Somebody has asked why Higgs field is not dark energy, and there are reasons for not doing that, not believing that. But also you will have more lectures, so you will hear more. If after all those lectures you still have queries, please feel free to write to me. Okay? So.
Thank you, ma'am. Thank you for sharing the mail with us. Now I would like to make few announcements. So it's regarding the instruction. So the instructions for Google Meet session, no questions will be allowed in between the talk. Please note down your question and ask at the end, and use the chat window properly, and do not discuss irrelevant things in the chat window. If you have any question, then write down in the chat box and wait for the moderator to respond, and only then unmute yourself. Use ear or headphones through the Google Meet session, and during the whole talk, disable your mic and video. So when you join the Google Meet, you will see a present now icon. Do not press it. it is not actually for attendance purpose. It is for sharing purpose, the screen share. So the entry in the Google Meet will be on the first come first serve basis, and the maximum participation limit for the Google Meet is 250. And after 250, when the lobby is full, you can join us on our YouTube session. And to see the presenter, to see only her or his screen, you can pin the presenter screen. And for YouTube viewers, if you have any question, then write down in the YouTube live chat box and wait for the moderator to respond. Also, there are traditional things like about attendance and certificate. I have shared the attendance, the participations list with you. You have to check the formatting and name of your institute, and as well as your name as well. And tell us if there is any correction to be needed. And there are lots of... Yes, ma'am. Just
Rajesh, maybe you can tell this thing to the participants later on, and we can thank Rohini before.
Yes, ma'am.
Yeah. So these instructions you can give to the participants later on.
Yes, ma'am.
Yeah.
So I thank you, Professor Rohini Godbole, once again for this enlightening talk. And hopefully we will get in touch with you in the near future.
Thank you so much, ma'am, for joining us.
Yeah, thank you, Rohini. Thank you so much. So we are really privileged to have you here, and hopefully we can invite you in person also at NIT.
We have been trying that. That has not worked, and now this pandemic.
Yeah.
This is not the first time you asked me to come, but the first time it has worked. At least thanks to internet.
Thanks to internet.
Yeah. As I said, you can announce and you can actually tell them to write. I don't mind. Okay.
Yeah, definitely. I'll share the address and then we can.
All right. And I will send you the Google Drive link to the talk so that you can.
Okay. Definitely. I'll.
Bye. And good luck with your program. And all of you, hope you enjoy it.
Yeah, thank you so much. Thank you.
Thank you very much.
A lot.
Bye.
So before ending the session, I would like to just say 2 lines. Participants, everything is updated on our website. So it is good practice to check the website before asking on the WhatsApp. So kindly be patient and wait for the website to load properly. Also, usage of laptop is recommended. So all the important links are updated in the group description, and I am repeating again, everything is updated on the website.